Welcome back. Today we are exploring optimization for deployment, how to make LLMs practical, efficient, and cost effective for real world applications.
Deployment is where research meets reality. A model that works in the lab needs to work at scale for real users.
Let's start with latency. What is it and why does it matter?
Latency is the time from when a user sends a request to when they receive a complete response. For interactive applications like chatbots, low latency is crucial for good user experience. Users expect responses within seconds, ideally under 2 seconds for the first tokens.
But generating text autoregressively is inherently sequential. You can't generate token 100 until you've generated tokens 1 through 99.
This makes latency challenging, especially for long outputs.
Let's talk about throughput versus latency trade offs.
Throughput is how many requests you can handle per second.
Batching multiple requests together increases throughput but can increase latency for individual requests.
The optimal balance depends on your use case.
For interactive chat, you prioritize latency. For batch processing tasks, you prioritize throughput.
Now, let's discuss model size versus performance.
Larger models generally perform better but are slower and more expensive to run.
For deployment, you often want the smallest model that meets your quality requirements.
This is where techniques like distillation, quantization, and pruning come in.
You sacrifice some quality for significant efficiency gains.
Let's talk about quantization in more detail.
Quantization reduces the precision of model weights and activations.
Instead of 32-bit floating point, you might use 16-bit, 8-bit, or even 4-bit integers.
This reduces memory footprint and can speed up computation on appropriate hardware.
Post-training quantization applies after the model is trained.
Quantization aware training includes quantization during training, often giving better quality.
FP16 and BF16 are 16-bit formats with minimal quality loss and are widely used.
INT8 quantization can give 4x memory reduction with careful calibration.
INT4 and even lower precision are emerging, though they require more sophisticated techniques.
Methods like GPTQ, AWQ, and QLoRa optimize quantization for different use cases.
Let's discuss caching strategies.
The KV cache stores key and value vectors from previous tokens during generation.
This avoids recomputing them, dramatically speeding up autoregressive generation.
But the KV cache can be very large for long contexts or large batch sizes.
Cache eviction policies decide what to keep when memory is limited.
You might evict the oldest tokens or use attention patterns to identify less important tokens.
Some systems use sliding window caches, only keeping recent context.
Multi-query attention and group query attention reduce KB cache size by sharing across attention heads.
Now let's talk about serving systems.
Systems like VLLM, TGI, or RayServe are optimized for serving LLMs in production.
They handle request batching, KV cache management, and efficient GPU utilization.
Continuous batching dynamically adds and removes requests from batches as they complete.
This keeps GPUs busy and improves throughput.
Page attention in VLLM treats the KB cache like virtual memory, reducing fragmentation.
This can increase throughput by 2 to 4x compared to naive implementations.
Let's discuss model parallelism for inference.
Large models might not fit on a single GPU, even for inference.
Tensor parallelism splits layers across GPUs.
Pipeline parallelism splits layers vertically.
The right strategy depends on model size, hardware, and latency requirements.
What about CPU inference?
For smaller models or lower throughput use cases, CPUs can be cost effective.
Quantization is especially important for CPU inference.
Libraries like llama.cpp optimize LLM inference on CPUs.
This enables running models on edge devices, laptops, or CPU only cloud instances.
Let's talk about cost optimization.
Inference costs scale with compute, memory, and bandwidth.
Reducing any of these reduces cost.
Smaller models, quantization, and efficient serving all help.
Auto-scaling adjusts the number of replicas based on load.
During low traffic, scale down to save cost. During high traffic, scale up.
Spot instances or preemptible VMs can reduce cloud costs but require handling interruptions.
Some applications use model cascades. Try a small fast model first and only use a large model if needed.
This saves cost by routing easy queries to cheap models.
Let's discuss API design for LLM applications.
Good API design balances flexibility and simplicity.
Parameters like temperature, top at, and max length control generation.
Streaming responses improve perceived latency by showing tokens as they're generated.
Timeouts and rate limiting protect against abuse and manage load.
Error handling is important. Models can fail or take too long.
What about model versioning and updates?
You'll likely improve your model over time with new training or fine tuning.
How do you deploy updates without breaking existing applications?
Versioned APIs allow clients to specify which model version to use.
Blue green deployment runs old and new versions simultaneously, gradually shifting traffic.
Canary deployment sends a small percentage of traffic to the new version first.
Monitoring both versions helps catch regressions before full rollout.
Let's talk about safety and moderation in deployment.
Production systems need guardrails to prevent harmful outputs.
Input filters can block or flag inappropriate requests.
Output filters check generated text for policy violations before returning it.
Some systems use classifier models to detect toxic, biased, or unsafe content.
Others use rule based systems or manually curated lists.
There's a trade off between overfiltering, which limits usefulness, and underfiltering, which allows harm.
Human in the loop systems flag uncertain cases for manual review.
Now let's discuss monitoring and observability in production.
You need to track latency, throughput, error rates, and resource utilization.
But also model specific metrics like average output length, token generation rate, and cache hit rates.
User feedback is valuable. Are they satisfied with responses?
Some systems log all interactions for later analysis with appropriate privacy protections.
Dashboards visualize key metrics in real time.
Alerts notify engineers of anomalies like latency spikes or quality degradation.
What about A B testing for LLMs?
You can test different models, prompts, or generation parameters with subsets of users.
Measure which variant performs better on key metrics.
This could be explicit feedback, task completion, or engagement.
A B testing helps optimize the deployed system iteratively.
Let's discuss edge deployment.
Some applications need to run on devices, phones, laptops, or embedded systems.
This requires very small models, aggressive quantization, or specialized architectures.
The benefits are privacy, low latency, and no internet dependency.
But model quality is limited by device capabilities.
Techniques like knowledge distillation and neural architecture search help create efficient edge models.
What about hybrid architectures, combining edge and cloud?
Simple queries run on device. Complex ones are sent to the cloud.
This balances latency, privacy, and quality.
Finally, let's talk about the full deployment lifecycle.
Training and deployment are iterative, not one time.
You deploy, monitor, collect user feedback, identify failure modes, improve the model, and redeploy.
Continuous improvement is key to successful LLM applications.
Data flywheel effects can emerge. User interactions generate data that improves the model, attracting more users.
So, to recap, Deployment optimization balances latency, throughput, cost, and quality. Quantization and efficient serving systems are crucial. Caching and batching strategies improve efficiency. Safety filters and monitoring protect production systems. And deployment is an iterative process of monitoring and improvement.
Next episode, we're exploring open source versus proprietary LLMs, the different models of AI development.
Thanks for listening.
Until next time, keep learning and stay curious about